Welcome back to the hyperbolic heaping chamber. We are back once again. I have to say it, the developers and content teams at LeetCode are becoming very, very skilled at creating very, very torturous amounts of content. So the heap content has been hard to get through. Actually, the Explore card wasn't bad, but the Geeks for Geeks content, they might be at the cutting edge of hard to understand content. But fortunately, we had someone in the Discord, shout out Pew Pew Pew, send me some pretty cool resources for to learn. But at the same time, I'm realizing I'm feeling some angst. And I think the angst, it's not really angst, I think it's more frustration. Because I'm starting to think there's a part of my brain that thinks the most perfect way to do this is to learn how to implement the heap at will, right? The hard way. But at the same time, doing this is kind of making me want to die. So maybe that's not the best way. So maybe the way where things have to go exactly the way I envisioned it is not the right solution. This would all be solved if we just used Python or C++. I think C++ is dead. There's just too much syntactic nonsense. I used to use it a lot in college. It's a really cool language, but something about fighting with the syntax all the time just became very frustrating. Python is the best interviewing language, hands down. So maybe we just have to accept it. Maybe we just have to become Pythonic peoples and accept our fate. Because, I mean, at the end of the day, it's just a tool, right? And I think that's important because I wanted as a theme where I kind of want everything to be exactly how I imagined it. I wanted to constantly be using JavaScript and TypeScript, but maybe it don't make sense. So maybe in the case where the problems require heaps, we'll just switch to Python. In the cases where the problems don't require heaps or a deck, we'll just use JavaScript. That being the case, I think a lot of the problems that we're struggling with will be symptoms of the past if we just go forward with that. So I'm thinking that's what we're gonna do. Part of me wants to do it the hard way, but the hard way is burning me out. So I think we learned a lot by trying to implement it the way we did. Now I get the two properties. There's the heap property and the complete binary tree, and there's ways to represent it. I think all that stuff is really important. But what I was doing before, in my head thinking that I was going to implement it on the spot every time, is there a point to doing that other than making the grandmasters quake in their shoes? There might not be. So that being the case, I think we're going to get back to solving problems. We spent like 4 or 5 days on the heap thing. So if the problem requires a heap, we're just going to straight up, if the problem requires a heap, I think we're just going to switch to Python, accept our fate. If it doesn't require a heap, if it requires a heap or a deck, we're going to do that. If it doesn't, we're just going to roll as usual. So that being the case, I think we're going to do a slightly shorter session today, or at least the minimum I'm going to commit to is 30 minutes, just because we've been struggling on brain sauce, but I don't think there's a big problem with that. And yeah, so I think 30 minutes is fine for today. Oh yeah, we also have some comments, so we have to make sure to check those out as well. I think we have comments. Oh, so we have a comment from Ashes of Osiris. Bro, how the room getting messier though? True, actually true. Okay, so there's a story behind this. Where I'm in talks with. I was just in the VC last night with some tech execs, and we're just building something right now. And my place is just a storing place for some of this stuff. So it just be what it is sometimes. But yeah, that's really funny. This is the storage room. So this is the storage room. And I doubles, it's not really an office, but it's really a storage room. So that is really funny. So we'll try to see how far we can take the room. And we might have to take it to the peak. And then we have Ice Cream Man 157 says, skip a day, I dare you. So yeah, honest, we might just skip a day just for the sake of skipping a day. But nah, we can't, man. We can't. a little a day goes a long way. So that's kind of where we're at. But honestly, we might have to. But honestly, man, we're just trying to get like ice cream, man. So if he skips a day, then we'll skip a day for certain. That being the case, I think we're gonna lock in for 30 minutes to get back to problem solving. My brain hurts because we spent 5 days on heaps, and I gotta keep it 1,000. It was important for us to focus on learning, but at the same time, there's a part of my brain that just wants the number to go up. We all got that brain, that lower level in the brainstem where it's just animal. It's just full animal tendency, and we like when number go up. So I wanted to see the total number of problems done go up, and it hurts that the last 5 days they haven't gone up by that much because we've been learning. It is what it is. That being the case, we're logging back into the jet stream, and we're gonna start cranking out problems. So that's where we're at. We're gonna log in for a nice 30-minute banger, maybe longer if we're feeling it. And I think yesterday we were working on solving a problem, and I think we did solve it actually. I think we used regex. Yeah, I think it was called type something. Oh, it was this one. It was long press name, and we just used regex to do it. Now there's definitely a 2-pointer pattern in here somewhere. The way that they would do it though, I'm not exactly certain how, but it seems to be a relatively popular problem. So I'm satisfied enough with that, but it's kind of hard to know how long the time complexity would be. So I think we can cross this one out. We have a problem called number of arithmetic triplets. So you're given a 0 index, strictly increasing integer array. Okay, I think strictly increasing means that every element is unique. And a positive integer diff. A triplet I, j, k is an arithmetic triplet if the following conditions are met. I comes before j, which comes before k, and num sub j minus num sub I equals diff, and k minus j equals diff. So 1, 4, and 7. Oh, return the number of unique arithmetic triplets. So a diff of 3, right? 2 minus 1. Oh, 1, 2, 4 means the actual indexes. One, 2, 4 means the actual indexes. So it means the actual number of indexes. I mean, this means it's actually the indexes. So we say 1, 2, and 4, we mean 1, 4, and 7, right? Which makes sense. And then can we also get 3 again? We have 1, 4. I'm actually not seeing how you get it again, but they say with 2, 4, and 5. So 0, 1, 2, 4. Oh, with 4, 7, and 10. Okay. Well, interesting. Determine the number of arithmetic triplets. Okay, so what is the maximum length we can expect from nums? Nums length is greater than 13, so we can pretty much eschew any point of, we can eschew any exhaustive, any ideal where we would generate all possible versions. Now it's strictly increasing, so maybe there's some way we can use that. If it's strictly increasing, it means that the remaining numbers that would create the triplet are past the current index. So if we iterate through, right, we would keep iterating, right, until we'd find something like num sub I plus 1 minus num sub I gives you diff. We'd find this first case to be actually no. If for 0, we iterated through the entire array of numbers and found if any of them had a difference of 3, we would find that we have no answers for 0. If we did the same for 1, we would find that we do have one pair which gives us a difference of 3, which would give us both of those values. Then we go for 4, we'd only find 7 and 10. Now my question is, how could we tie this all together to calculate the number? One and 4, 4 and 7, and 4 and 10. What if we assume that every individual pair actually, we could count it simply. If we generate all those values, we can just say, okay, we know that 1 to 4 gives us that diff, which means that the final indice must exist afterwards and give us a difference of 3. If that's the case, we could reach into some sort of map which would give us all the remaining combinations starting at 4 that would give us a number ending at 3. I mean, a difference of 3. If we did it that way, this could make a lot of sense. Because then we'd find, for category 1, we'd pretty much generate a map that would look something like this. So for the starting index 1, we know that we can get a difference of 3 if we go to these particular indexes. 2, and that's about it, right? Then from here, from 2, we know that we can get a difference of 3 by going to 2 indexes, right? Actually, zero, 1, 2, 3, 4. Yeah, let me actually write this out. So if we wouldn't have anything in the array for 0. We wouldn't have anything else for 1. For index 2, we wouldn't have anything else coming out to difference of 3. For index 0, 1, 2, 3. Just 6, we wouldn't have anything. For index 5, 0, 1, 2, 3. No, 0, 1, 2, 3, 4. We would know that using index 10 would get us a difference of 3. think I'm slightly confused. 0, 1, 2, 3, 4, 5. Oh, I think I see what's happening. 0, 1, 2, 3, 4. Let's go to index 5. So we have 1, 2, 4. It feels like our algorithm would run n squared time. Because we need to generate all the... Oh no, wait, we don't need to generate... No, wait, this could run in linear time. Because you can only check the ones in front of you. So for 0, you would just say, okay, well, 0 minus 1, 1 minus 0, 4 minus 0, 6 minus 0, 7 minus 0, 10 minus 0, and then we'd slowly go down. And that would just be linear time. So let's break this down into the map, which is going to be a map of index to an array. I don't think we're ever going to get an array of numbers. If the array is strictly increasing, that would mean that there would be two ways to subtract a number from another number and get the same difference. Which means if I can subtract 4 minus 1 and get 3, to get an array of numbers, it would have to mean that I could subtract another number minus 1 to get 3, and that's just not possible. So we don't need access to an array. Each indice is going to map to 1, and then we should be able to check in linear time. First we have to populate this array, this map. We'll run while I is less than nums.length minus 1. So we'll skip the last element. And then we're basically just going to do an inner loop, and this shouldn't be n squared time because we're not going to do n operations for every element. We're only going to do n operations for the first element. And then and then this second inner loop is actually going to be the value j. J is going to equal to I plus 1, so that we don't have values equaling itself. And then I think we should be good to implement this. Let me sit up. And then I think to set this up, we just have to say map.set. First, we have to say, right, if num sub j minus num sub I equals diff, and we're going to say map.set index I to index j. And I think that's all we should have to do. Then we're going to have a value called count, which is going to be equal to 0. We're going to do for const I guess we can say for I and j, right, of map. This is how we'll check count, right? Everything in the map gives you a difference of everything in the map, right? Its value subtracted by its key should give you a difference of the ideal difference. And the way we'll know to increment count is if I is if we get j, right, j dot, we do map dot get the value for j. If map has a value for j, then we'll do count plus equal 1. Nice. So this should run in linear time, I believe. Should be linear time in linear space. In fact, couldn't you just... You could get rid of the map entirely. And then in here we could have another loop. Should be K, which would equal to J plus 1. Should still give us linear time, I think. I think this other version is slightly slower. This is the same one we had. That's actually really interesting. It looks like you can get linear time with constant space. It's not that the array is sorted, but you can simply just check if the number in the array subtracted by the difference exists, and that number subtracted by the difference also exists, and you'd find numbers that exist. To make that make sense, you need a map. That's really cool though. So we'll go to maximum nesting depth. I think we did this already. We have largest local values in matrix. Did we do this already? Already did this one already too. So let's try best poker hand. Rank transform, count good triplets, first letter to appear twice, and backspace string compare. So you're given an integer array ranks. You're given an integer array ranks. I hate card questions because I don't play cards. You're given an integer array ranks and the character array suits. Integer array ranks. Integer array ranks. Okay, so it's an array of integers, and the character array suits. You have 5 cards where the ith card. The ith card has a rank of ranks of I, and the suit of suits of I. You have 5 cards where the ith card has a rank of rank Savai and a suit of suit Savai. Yeah, I don't get cards at all. 5 cards of the same suit is a flush. 3 cards of the same rank. What's a rank? So ranks are the numbers. So 3 cards of the same rank. Pair 2 cards of the same rank. So 2 cards of the same number. High card. Any single card. Return a string representation representing the best type of poker hand you can make with the given cards. Values are case sensitive. So all these are 13 of A being some kind of suit. And the best hand is 5 cards of the same suit. The next best hand is 3 of a kind. The hand with the first, second, fourth card. 3 of a kind means 3 cards of the same rank. No 2 cards have the same rank. So it looks, couldn't you just return each one? So we'll just say five cards of the same suits. Do suits.every, right? S is equal to suits. Can return flush. Also, if 3 cards of the same rank. I wanted to figure out a way to check it in one line. And we'll save. if two cards have the same rank. So two cards have the same rank. We can get this by checking if the map dot size is less than 5, can return pair, and then at the end we can return I card. So we'll take that, and I think we will stop there for today.